Good morning, everybody, and welcome to this session. I'm Viresh Kumar, and I work for Linaro. We'll be talking about what we have been doing in LNG for past couple of months around the work on isolating the core and with the help of know-how sensitive sets. So we'll be discussing why do we need to isolate CPUs in the beginning. Why is such a requirement there? Isolate from what exactly, and then how to isolate, and how to confirm that yes, we are able to isolate or not. So why to isolate? In the networking domain, we can broadly classify the domains as in control plane and data plane. Control plane is more about controlling the packet processing and all, and it doesn't require that high performance capability. And then we can use something like CPU flag and CPU adder and all there to manage power efficiently for those use cases. But in the data plane side, we'll be packet processing all the data packets, and that has to be done at a very high speed. And even a very small lag will not be tolerable at all. Similar requirements are also true for high performance computing and real-time systems, where they really can't tolerate any kind of disturbance from the kernel. So in today's kernel, every CPU is you can say pinged by many, is stopped by many surrounding things at multiple time events. At that time, context switching happens, and the task is placed to wait queue, where it will wait for some time, and then it will get the chance again to run. There are so many sources of these interruptions, and that we have to get rid of all of them. The main of these are other tasks which are running on a system. So scheduler runs on every CPU in a system, and at that time, the scheduler might try to migrate some other tasks from other CPUs to this CPU, or some other CPUs may decide to push some tasks to this place. That is called load balancing. And if some other task comes to this CPU, then the current thread, the data plane thread, will not be able to run for full time. It has to give the CPU to other threads as well. So that's why we have to migrate not migrate, but isolate the CPU from all the other tasks that are running in the system. So idea in the data plane side is that so the SOC will be a big one, so it will have so many CPUs, like in thousands something, and we can dedicate a single CPU for each data plane thread. And we want that individual data plane thread to run on that particular CPU for as long as it wants. There should not be any interruption, there should not be any context switching, and nothing at all. The other source is the kernel, the interrupt from all the hardware peripherals. By default on ARM, they are probably affine to CPU 0, but yeah, they can be passed to the CPUs as well, and we have to take care of them as well. Kernel tick is one of the biggest source of interruption. So for schedulers and kernel's internal functioning and for handling the multiprocessing part of it, the kernel runs a timer called as tick. So it runs at a tick rate. So there's a variable called hertz. If the value of variable is like 100, so we will get an interrupt at 1 by 100 milliseconds. Right? So at 10 milliseconds, 1 by 100 seconds. So it will be like every 5 to 10 milliseconds we'll be getting an interrupt from kernel. At that time, the schedule will come into picture. It will see if I need to run some other task or not. I have to service some work queues, timers, HR timers, and all that. So that kernel does this. So every 5 milliseconds we get interruption, and the data can't tolerate this at all. Because 5 milliseconds is a very small time. The other sources of interruption are timer, HR timers, and work queues. These are used partly by the core frameworks as well, and many times by individual drivers. So if some driver want to delay something or they want to schedule something for the future, in all these cases they use timer, HR timers, and work queues. All these can be pinned or unpinned. What do I mean by that is a pinned timer should fire on a particular CPU. That's a requirement of the code. Otherwise, it may not work properly. And there are unpinned timers which can actually fire on any CPU, but because the way kernel booted or because how the timer is initially queued, it might have got queued to the CPU we wanted to isolate. And so there might be timers and HR timers which might fire on the isolated CPU, and that will cause trouble as well. So many of these can be isolated using the existing kernel features which are already there in the kernel right now. So suppose from task, there is something called CPU sets in kernel. So a user can work with CPU sets from the sysfs level, from the user space level. We don't really need to change the kernel at all for this. It's as simple as like creating some directories in the user space and then allocating resources to those. And resources, by resources I mean memory and CPU and some other things as well. So what we are doing here is we are creating two CPU sets, one for the data plane threads and one for the control plane threads. So we can allocate some CPUs to the data plane block and some CPUs to the control plane block. Now, because we want the data plane threads to run continuously on a particular CPU without interruption, we want to disable load balancing completely there. So what we do is, so I don't have a diagram here, but suppose this is a control plane CPU set and this is a data plane CPU set. We disable load balancing between them so that nothing migrates from the control plane block to the data plane block. And within the data plane block, there can be multiple CPUs, so we disable load balancing between them as well. So that within the data plane CPUs as well, we don't migrate tasks, right? So a task which is started on a data plane CPU, it will stay there till the time it ends, and nothing else will come and run there, right? So even when a new task is created by an existing task, it will run on the CPU set on which that task is. So suppose a task in the control plane CPU set creates a new thread or task, it will stay in the control plane, it will not get migrated to the data plane because we have disabled load balancing. Most of the interrupts can be assigned to a particular CPU. So they are all assigned to the control plane CPU, and we don't have any of those assigned to the data plane CPUs. But there are some interrupts like the PPIs and the like IPIs and all, which have to come to that CPU so that it can open up later on. So those can't be migrated, but they will be used later on if required. But they wouldn't ping, without any reason, unless some CPU wants to talk to this CPU. This one is probably the most important one because there have been quite some work around this. So in kernel, so I've already told you about the feature hertz. So at hertz rate, kernel gives a timer is programmed to give interrupt to the kernel for all the CPUs. So there will be an individual timer for every CPU. So there is a feature called Hertz, no Hertz idle, and no Hertz full. In no Hertz idle, what we do is, in case a CPU is sleeping or it is idle, we stop the tick at that time, so that we don't wake it up to just service the tick, right, at 35 milliseconds. That was there in the kernel since a long time, and it is working very well. Probably no issues around that. Then a new feature was added almost completely in 3.10 kernel, uh, which is called no Hertz full. So the concept of no Hertz full is that if there is only a single runnable task on a particular CPU, we can stop the tick for some time, right? The idea is to stop it forever till the time there is only one task on that CPU, but due to some kernel constraints right now, it is limited to 1 second interval. So instead of a 5 millisecond timer tick, we are getting that interrupt at 1 second now. That feature is also there in the kernel, but there were many bugs around that which we have to solve to get things working. So the bugs around that were even even with no Hertz full, we really believe that the tick have been stopped, and we will get an interrupt at 1 second now instead of 5 milliseconds. But there was a bug that on most of the architectures, I think, probably Intel, ARM, and PowerPC as well, that we are still getting spurious interrupts at 5 millisecond rate. So the tick is actually running, but the kernel is not doing anything about it. The problem is that so internally there is a clock event device which the scheduler core uses to program the hardware timer, and we are not actually stopping that clock event device when we stop the tick. Because of that, the timer is firing the interrupt every time, but the kernel sees that there is no HR timer enqueued, and I don't have anything to do, so we just return back from the interrupt handler. But we are getting an interrupt every 5 milliseconds. So me, Kevin, are actually trying to upstream some changes to the kernel to fix that bug. But there have been quite a big change actually around that part. So it's taking some time to get upstream. But otherwise, we have a local solution with that, and we have got rid of all those previous interrupts, and things are working very smoothly now. There were some other bugs actually that in no Hertz full mode time, because we have stopped. So the tick is very important for many aspects, like for scheduling all the timers, HR timers, work queues, and even migrating tasks around or doing the multi-programming thing. So if the tick is not there, all this would not be done. So they have to be there should be some special care taken for all of them. There were bugs around this that if we are in no Hertz full, if we add a new timer now, it will not get scheduled at all. So it will wait till the time tick will come back. So I have sent many patches for them, and probably these are all gone. So they are all merged into the kernel, and they are fixed in the mainline kernel now. Now there is, so as I told you earlier, there are timers and HR timer framework in kernel which are used by the core frameworks and by some of the drivers for the functioning, for scheduling work to be done later, right? So now there are two categories of those, pinned and unpinned. Pinned should fire on that particular CPU, but unpinned can fire on anyone. But we don't want any unpinned timer to fire on a isolated core, right? Because it can actually fire on a control plane CPU. We don't want really it to fire on a data plane CPU and break our isolation. So we had a chat with upstream maintainers earlier, and Peter Jestra, who is the scheduler maintainer, he asked us to change the CPU set code and add a quiet option there, so that when we echo 1 to that particular file, all this background activity, which is not really important to be fired on that CPU, can be migrated away to other CPUs. So we have actually added a quiet option. So when we echo 1 to that, all the unpinned timers and HR timers are migrated away to the control plane CPUs. So in the kernel, for that we make a list of CPUs, make a list of timers and HR timers which are pinned, which are unpinned, and all the unpinned are migrated away. So that's what we are doing. We have also sent these patches to upstream, but because of the other patches, they are still blocked, and we actually haven't gotten much review comments on them yet. In a similar way, there are work queues. So for work queues, actually, a guy from Red Hat, Fredrik Weisberger, has been doing some stuff. to control work queues to particular set of CPUs from user space only, from the sysfs interface. And this has been merged, I think, but I haven't tested it yet. But you have been doing something there.
I'm pretty sure it's merged. I haven't tested the actual merged version, but I did test several of the series that were posted while they were in progress.
Okay, so that should work as well. Now, it's a big question actually, how do we confirm that isolation is, a CPU is really isolated? Because you really have to either run something like ftrace or tracemd to see what's going on a CPU exactly at the very smallest level and see if